Hello friends, welcome to Web Academy. In the last series of lecture, we have completed the discussion on the D'Alembert's principle. So in this particular lecture, we will start discussing classical mechanics. So mechanics is basically divided into three branches. So the first one is the classical mechanics, that is also known as Newtonian mechanics, because it deals with the Newton's laws of the motion. Second one is the statistical mechanics, and third one is the quantum mechanics. So in the classical mechanics, we have basically deals with the Newton's laws of motion. In classical mechanics, we assume that suppose we have a rigid body, so we assume that the entire mass of the body is concentrated at the center of mass. So we do the analysis of the center of mass based on the Newton's laws of motion. In statistical mechanics, we do the analysis of each and every particle of the body. Suppose we have 10 to the power n particles, so we do the analysis of each of these 10 to the power n particles. Now in the case of quantum mechanics, we do the analysis of the microscopic level. At microscopic level, we mean we do the analysis of subatomic particles like protons, neutrons, and etc. Obviously, in case of the analysis of the subatomic particles, we do not use the Newton's laws of motion. So this is basically the drawback of the classical mechanics, that is does not apply on the microscopic particles. Okay, so based on this drawback, there was the further invention of the quantum mechanics. Okay, so now let us go through the difference between the classical mechanics and the quantum mechanics. So the classical mechanics deals with the study of macroscopic objects like planets, stars, etc. In the case of quantum mechanics, obviously the analysis is at the microscopic level. So we have, it deals with the study of microscopic particles like electrons, atoms, molecules. Classical mechanics is based on the Newton's laws of motion. That's why we call this as Newtonian mechanics. In quantum mechanics, we have, it is based on the Schrödinger wave equation. The Schrödinger wave equation is H psi is equal to E psi, where H is the Hamiltonian operator. In classical mechanics, it is based on the particle nature of the object. In quantum mechanics, it is based on dual nature of the objects. Okay, so by dual nature, we mean particle-like property and wave-like property. Just like light exhibits both these properties. In classical mechanics, everything can be measured with 100% accuracy, and it is based on the deterministic law. By deterministic, we mean suppose we know the initial condition, so based on the initial condition, we can arrive at the final condition. Suppose we have the equation of motion as v is equal to u plus at, and we know the initial velocity, so we can find the final velocity. Hence, based on the initial condition, we can arrive at the final condition. This is known as deterministic laws. So in classical mechanics, we have energy is absorbed or emitted continuously. Okay, so suppose we have thrown an object in the space. Okay, so here kinetic energy is getting converted into potential energy. Hence, energy is absorbed or emitted continuously. In quantum mechanics, the energy is released in the form of packets called quanta. Okay. In fourth point, it was based on the deterministic law. So in quantum mechanics, we cannot measure everything with 100% accuracy. So it is based on the probability. Okay. Now in case of classical mechanics, we do the analysis at macroscopic level. Obviously, larger units like kilometer, kg are used. In case of quantum mechanics, we have smaller units like angstrom, nanometer, etc. In classical mechanics, it fails to explain the energy matter relationship. Okay, so there is no relation between the energy and matter in case of a classical mechanics. In quantum mechanics, successfully explains the energy and matter relation. The Einstein has given E is equal to mc square, which successfully explains the relation between energy and matter. In classical mechanics, it deals with matter without considering the atomic or molecular structure, because we do the analysis at macroscopic objects. Okay, so here we do not consider subatomic particles. In case of quantum mechanics, it deals with the matter considering the atomic or molecular structure. Okay, so now let us go through the challenges that led to the discovery of the quantum mechanics. So what were the challenges in the classical mechanics? Okay, so we have the challenges in the classical mechanics. So first one is at relativistic front, and second one is at the microscopic front. So the Albert Einstein figured out that when the motion of a body is at the speed of light, okay, so something is moving at a speed of light, then the Newton's laws of motion are not applicable in this case. Okay, so this led to the discovery of the quantum mechanics. Okay, so at the relativistic front, we have in 1905, the Albert Einstein figured out that the Newton's laws of motion are no longer valid at the relativistic speed, that is speed close to the speed of light. So suppose something is moving with a speed that is close to the speed of light, then the Newton's laws are not valid in this case. Okay. Secondly, we have the microscopic front. It was figured out that the classical mechanics cannot explain the motion of subatomic particles such as electron and neutrons. Okay, so in case of the motion of the subatomic particles, the Newton's laws of motions are not valid. Okay, so based on these two drawbacks, this led to the discovery of the quantum mechanics, because the Newton's laws of motions are not valid in these cases. Okay, further there were various experiments like Young double slit experiment, black body spectrum, we have photoelectric effect. So these experiments also were not analyzed with the use of the Newton's laws of motion, because classical mechanics is not valid here. So all these issues, all these drawbacks led to the invention of the quantum mechanics. Okay, we will discuss further in next particular lecture. Thank you.